Chapter 8, Section 1, Systems of Equations in Two Variables. Well, they kind of drill right into word problems to really highlight how powerful this is when we can do a system. A system is in this case that we're going to focus in on are two lines. Really, we're going to have an equation. We end up with translating stuff into equations. We did a little bit of that in chapter 3. And, we had all these ways about taking data, really, and taking the ordered pairs, and we did a lot of techniques on how we can create equations from that. When you have an equation, basically you can pull out different solutions, and if it's has two variables, there's an infinity of solutions. So we went through a whole chapter about how do we graph that, how do we draw pictures of that. Well, really all that is new in chapter 8 is that we're going to run into multiple lines, and we're going to focus in on when we have two linear things that happen. And what's very powerful about this is that it gives us a methodology, or basically a way to solve more complex problems. And that's why they drill right into examples here. They're going to have some things about, they're going to review the strategies on word problems like familiarize, translate. But the goal here is you need to remember we're trying to create equations. And these equations in this case will have two variables. And that's what they're talking about, is when you have a system of equations, we're basically looking for a solution or multiple solutions that will work for both of these equations. So a solution to the system is something that works in both of those. And we're going to show a couple things here that they do that. And why, again, they drill right into a word problem, which is usually your harder part of the section, is that they want to really see how powerful this is. So let's look at this first example of endangered species. It says in 2012 there were 92 species of birds in the United States that were considered threatened. And what they, in parentheses there, they have this thing likely to be endangered, right? So that's what threatened means in this conservation scenario. Or endangered, which is the next stage, which is they're in danger of becoming extinct. In other words, at that point there's none of them left. So the number of species considered threatened was 3 less than 1/4 the number considered endangered. Write a system of equations that models the number of U.S. birds considered endangered and threatened in 2012. Well, we need to reread this thing. And when you familiarize yourself with things like this, one way to do that, you look at it, you're going to pull out, you need to translate what the words means as far as operations and those kinds of things. Well, one way to do that kind of helps write this thing is define the variables. Well, we have that kind of stuff, and what are they asking here? Usually that's where we get that. It says write a system of equations that models the number of U.S. bird species considered endangered or threatened. So they're looking for endangered and threatened. So let's define the variables to represent those two things. And that's what they do here. It says first, let's let T represent threatened, because they use T probably because it starts with a T. And let D be the number of endangered, which is, they don't use E in this case, because E, when you get into farther in mathematics, that's actually a constant, kind of like pi. So, but they use these two variables. Now, why is that important? Well, let's go back and reread this thing with the variables in there. There are two statements to translate. First, we look at the total number of endangered or threatened species of birds. Okay? Well, there isn't a statement there that tells us something in here, and it says there were 92 species of birds in the United States considered threatened or endangered. In other words, whatever those values are for each one, they add up to 92. So we create basically an equation. The threatened plus the endangered will equal 92. A lot of times that's the one that's hard to see sometimes because we kind of get focused in on the tougher translation and we kind of miss the easy equation. But that's how we'd get this first equation. We have a two variable equation. There's no exponents or any degree changes in our terms. So this is a linear equation. And just to quickly summarize that from chapter 3, what does that mean? That there's an infinity of solutions for this. Now, it would be kind of iffy because we don't have fractions of birds or fractions of species usually. So I wouldn't say there's an infinity. But if I had 0 threatened, for this to work, we'd have to have 92 endangered, because 0 plus 92 is that. But if I had 1 threatened, this would have to be 91, because it has to add up. Remember how many solutions there are that can occur. If you graph these values I'm talking about with ordered pairs, where probably if we follow the rules, the D would have to come first because of alphabetical order, we'd have an infinity of ordered pairs that would occur. And that would, if you drew a line through those ordered pairs, it would form a pattern showing a line, right? So every line on every ordered pair, on that line would be a solution to this equation. In other words, it makes it true. You know, and I'm saying a lot here, which just summarizes a lot of stuff from chapter 3 for review. Well, the second statement compares the two amounts D and T. If in the rewording in this and trying to get into a translation, well, the number of threatened species was, that is T is threatened species, is equal 3 less than 1/4 the number of endangered species. Be careful with that subtraction stuff. It has to be in the right order. 1/4 of D, 1/4 the number of endangered species is 1/4 D, and then I want 3 less than that, so you'd subtract 3. So we end up with this equation. T, threatened species, equals 1/4 endangered species, D, minus 3. So here's one equation with T and D in it. Here's another one with T and D in it. These are a system of equations. So what are they going to do with this thing? And that's kind of where they're going to go to first. Basically, we can translate things, we can get multiple equations, and that's what they're defining here. A system of equations is a set of 2 or more equations in 2 or more variables for which a common solution is sought. Not necessarily do you find that common solution, but we're going to look for that. Now here's another example with jewelry design. I'm going to spend a little bit less time talking about how we do this, other than this is very good to go through, I guess, is that, they familiarize, well, this drill that they go through here is what would we do if we knew numbers in here. They say they purchased 80 beads for a total of $39 to make necklaces. How many beads were sterling silver beads costing 40 cents each, and the rest were gemstone beads costing 65 cents each? How many of each type were bought? And translate into a system of equations. Now this is a different kind of problem, so we should probably go through this. It says familiarize. To familiarize ourselves with this problem, let's guess at the designer bought 20 beads at 40 cents each and 60 beads at 65 cents each. The total cost would be, and they put that in there, so I'd have 20 times the 40 cents and 60 times the 65 cents, which is 800 cents plus 3,900 cents, or 4,700 cents or $47. Well, according to what they just told me, that's too high. I need to guess and check. The other thing too, if you think about what you're doing here, well, how did I get this 20 plus 60? How did I know that these numbers is something that I'm going to guess at? Well, they have to add up to 80, right? Remember they tell us that there's a total of 80 beads. That's something to remember again, because we kind of get drilled into the tougher parts, and it's very easy to forget the simpler one, which is this equation right here, which is the silver plus the gemstones will add up to 80. Now we kind of practiced that in trying to familiarize ourselves with this. So we want to translate again by, let's define our variables. Let's let S equal silver beads and G equal gemstone beads. Since the cost of each bead is given in cents, the total cost is in dollars. We must choose which unit we're going to use throughout the problem. That's another place where it's really easy to forget this. You got numbers representing cents and some representing dollars, and you're going to come out with the wrong answer. So they choose to work in cents. So the number of cents, so the total cost of this thing, which they told us is $39, we're going to represent as 3,900 cents, 3,900 cents. The information in this table, and these tables are really nice things to organize with. They're saying, well, here's the number bought, and I end up with a certain amount of silver, that's going to be that variable S, and a certain amount of gemstone, which is G. Well, they both have to add up to 80. That's the easy equation usually, so I got the sum of those is equal to 80. Well, the price for each one, if it's in the silvers, right, I'm going to end up with 40 cents, and if it's gemstone, it's 65 cents. How would I figure out what's the cost for a number of silver ones? And what I would do is I take S, or the number of silver ones, like in this thing up here where they were talking about, they said 20. Let's guess at the number 20. Well, then you take 20 times 40 cents. Well, if the variable is S, then I take 40 times S, and I get 40S cents. If we remember, it's in cents. Well, the gemstones are 65 cents a piece, so the number of gemstones will be times the 65 cents, so you end up with this. It still has the variables in it, but what else do we know? We know when I add the total cost of the silver plus the total cost of the gemstone, I'll end up with a total cost for both, right, of $39. There's our second equation. Okay, kind of have a translation thing in here that happens, saying, remember, we got some issues, we got to create an operation around this to represent the total value or total cost of each type of bead. So we end up with these two equations. S plus G equals 80, and 40S plus 65G equals 3,900. Looks like I have a system again. So they basically go through some review on how to translate. That second problem is a little harder to translate. Very good tools to organize and set up our equations. But very key is that when I'm working on these things, that's exactly the methodology, or basically my strategy to figure this out, is to create equations with using the same variables or the same thing that could vary. Well, this next part is identifying solution. A solution of a system of two equations in two variables is an ordered pair. Well, that's how we have defined in chapter 3 that we're going to represent solutions in ordered pairs. But in this case, we want an ordered pair that will make both equations true. And if we have that, then that is a solution to the system. So let's look at example 3. So they give us an ordered pair of a -4, 7. And they were asking us, is this a solution to the system? Well, if it is a solution, then this ordered pair needs to make this equation x plus y equals 3 true. And it also needs to make this equation 5x minus y equals negative 27 true. And that's what they do here. It's kind of like the check. When I get an ordered pair and I want to make sure it's a solution, they put these, substitute this in, negative 4 in for x, 7 in for y, and they perform the operation to get 3 equals 3. So that's true. In other words, the ordered pair negative 4, 7 is a solution to x plus y equals 3. Now there's a lot of other solutions specifically for this equation, but definitely this is one of them. Now, so I'm halfway there. To find out if this is a solution to the system, this ordered pair also needs to be a solution or make this other equation, 5x minus y equals negative 27, true. Well, here's the work and the operations are done. They substitute in negative 4 for x and then 7 in for y, and they end up with negative 27 equals negative 27, which is true. So the answer to this is this ordered pair is a solution to this system using these two equations. Now, okay, so we could try that and everything else. This is a very good scenario to look at graphically. You know, if I can make a picture, draw a picture, or look at a picture illustrating some of these things, it's going to really help make some things clear, hopefully, and you can remember them. So basically they're going to go through that same problem where they were talking about this solution of negative 4, 7 is a solution to the system. We proved that by putting it into each one. But if we graphed each one of these lines like x plus y equals 3, you could use the intercepts, which is really easy to do. I could put 0 in for x and y would be 3, so I end up with the y-intercept, which is the x value is always 0, right? So I get 0, 3. If I want the x-intercept, I put 0 in for y and x equals 3. There's my x-intercept where it crosses the x-axis. Well, I draw a line through those 2 points. That's my line representing all the solutions to this equation, x plus y equals 3. Well, I would probably use the slope-intercept form for this one, just because it's more difficult to deal with that intercepts. So I'd add a negative 4 or 5x to both sides and take a negative 1 times both sides, and I'm going to end up with y equals 5x plus 27. So I have a 5 slope, and I don't have a very good y-intercept here. So I don't know if that was a good plan or not. It's telling me that with that equation, this line is going to cross the y-axis at 27, which would probably be up here on the top of this page someplace if I extended this line out. But if I can get a point, which I know is a point, but if I got the slope now, I do have a point. I know this point is a solution. I could use the slope of 5, which means I go up 5 and to the right 1, or I could go down 5 from there, which would put me down to here and to the left 1. Okay? Negative 5 over negative 1 is the same as 5. So I could graph that line. Well, when I say I have a solution to the system, usually we're looking at this intersection of these two lines is really where they have a common ordered pair, in this case negative 4, 7. So that's what we're going to do first. Now again, you know, kind of how chapter 3 started, we did a lot of stuff graphing, and so you could kind of solve some things with graphing, but it's not a very good method. Really what this is about is trying to make sure that you can see a picture of this. And by seeing this picture, you can see what it really means to have a common solution. And there's a couple different scenarios that can happen, and then we're going to talk about these as we go through. But most of the time, it's nice when we have an intersection of these two lines that are all the solutions of these single equations. When you have that intersection, that means I have one common ordered pair or one solution to this system. So example 4, they have these two equations of y minus x equals 1 and y plus x equals 3, and they start solving that, or basically graph those to find out where these lines are. So, and I'm not going to spend a lot of time going through the graphing. If you're having a little difficulty with that, that's all in the chapter 3, right? And I could use the intercepts here. I could put 0 in for y, and x would equal -1, which is this red line right here. And if I put 0 in for x, y equals 1. So there's the 2 points. If I drew this out, that's what that red line would be. In this one, I'd use intercepts again. The standard form is pretty easy to drop the points into these places. If I want the y-intercept, the x-coordinate is 0. Every point on the y-axis, the x-coordinate is 0. So I put 0 in there. Y plus 0 equals 3, or y equals 3. So there's your y-intercept. Your x-intercept would be 3, 0 right here. Okay, I draw that graph and I get an intersection. And it looks like, and this is a key part here, this one happens to fall right on the grid lines when I do this, so I have a pretty good clue by the picture that this ordered pair 1, 2 is going to be the solution to both. And then you need to check that. So you put 2 in for y, 1 in for x, and it makes this one true. 2 and 1, and makes that true. So this is the ordered pair that it's a solution to. Now another thing that can happen is you have parallel lines. And this is nice that they're in slope-intercept form, because what it means to be parallel, they have to have the same slope, which in this case they both have -3 as their slope. So they have the same slope, so they're parallel or lie on top of each other because they have the same rise and run, right? Well, if they have different y-intercepts, that's b here, portion of the slope-intercept form. So this indicates that 0, 5 is the y-intercept for this blue one, and this indicates that 0, -2 right here is the y-intercept for this other line. So we have the same slope, different y-intercepts. I have parallel lines. Now if I think about now, what does a solution to a system mean? If I look at this, is what it's telling me that there's no ordered pairs that are on this red line that ever cross this blue line. So there's no intersection, so there's no values that will be a solution to both of these equations. Another thing that can happen is that they are really the same equation or an equivalent equation. It's an equation that has exactly the same solutions, and like this one is 3y minus 2x equals 6, and -12y plus 8x equals -24. If you graph these two lines, you'd find out they're just exactly the same line expressed a different way. I can basically take and 1/4 times a -1/4, times both sides of this equation. I'm going to end up exactly with that same equation. But that's what's going on here. If I test this, and I tested points here, I could put the ordered pairs in, and it's going to say, hey, it makes them both true. But you need to realize, in this case, it is all the ordered pairs that are on that shared line are the solutions. So we end up with set notation, set builder notation, to say how do we illustrate or write down exactly what the solution is. And usually you take the more simplified equation and you have the set of x y, the ordered pair xy, such that 3y minus 2x equals 6. So all the solutions to this equation are a solution to the system. Now they bring in some more terminology here about consistent and inconsistent. Basically, if there's at least one solution, so there could be one solution or two or an infinity, it is called being consistent. So it has a solution, it's a consistent system. If the lines are parallel, like we just went through, there's no common point. There's basically really what it means, there's no solution to the system because they're parallel. This is called inconsistent. So having no solution or no shared ordered pairs between the equations means that they're inconsistent. Okay? If the lines coincide, like the last example we were talking about, but that's what it did describe. It says at least one solution that's consistent. Well, if I have an infinity of solutions, that has at least one, so that's consistent too. When one equation in the system can be obtained by multiplying both sides, basically they're saying they are dependent on each other. In other words, they end up being consistent because they do have a solution, at least one solution. But dependent ones are basically, what they're saying is they're equivalent equations. One side, is a multiple of the other one. So if I had an equation, if I took 2 times both sides, I'd have a new equivalent equation which has exactly the same solutions. And so dependency or dependent they're talking about in this scenario is that they actually lay right over the top of each other. And independent is for systems that have 3 or more equations that have, are independent, dependent, and so on. They're going to show us pictures here of this, which is nice because it's a lot of words to go through. If we look at this graph, which is a typical way, a lot of times this system is, so we have a graph of each line. They intersect at one point. We have this system. It is consistent because there's at least one solution, and it has that one solution. And then since neither equation is multiple of each other or a equivalent equation, they're considered to be independent. Even though they cross, right, or intersect, they are independent. Now graphs that are parallel, they give us these two equations again. This is what they would graph would look like, are inconsistent because they have no solution, and also they are independent. In other words, they're not multiples of each other, or they're not equivalent equations, another way to say it. So they're independent. So I can have no solution or inconsistent and still have an independent equation. I can have one solution, which still means that it is consistent because there is at least one solution, and I have an independent case because they don't lie over the top of each other. And then the last one they're talking about is actually dependent. And it also is consistent because when they are dependent, we have an infinity of ordered pairs that make both true. So some terminology to check and do that. Some of these can take a while to do, especially when you get into word problems. Graphing can be a little slower, but now we're kind of doubling the amount of graphing you do, and you're going to have multiple lines to graph to look at. And where we're going in the chapter is to get more away from the graphing as a solution, and there are some better ways to do that, especially when we're talking about fractional values. But that's the point here, is that we still need to get the idea of what's happening with systems with this graphing stuff. It's really to say, hopefully we can get a mental image, and then as you're working on other processes, it makes sense to know what they're doing.